Hello and welcome to the AI Digest. My name is Joaquin Melara. I am your host, and with me today is Axel Ngonga. How are you doing, Axel?
Oh, very well, thank you. How are you?
Great. And I'm a richer person just being able to meet you for the first time. You have a sunny disposition, and you're just I can tell you're just a ray of sunshine, ray of energy. You're just a positive person, and I really appreciate that.
I've been up to the same. I've been enjoying our conversation already.
So, Axel, you are a professor of data science at Paderborn University.
Correct.
And can you tell me a little bit about what you teach in that university?
Sure. So I'm in the Department of Computer Science, which means that I teach undergrad courses on programming, for example, or algorithm data structures is one of the courses I would love to teach. But in further studies, I teach knowledge graphs, semantic web, machine learning, or parts really of the machine learning course, statistical natural language processing. So really everything that has to do with taking data and giving structure to that data, injecting semantics into the data so that it can be used in downstream applications.
And what was your background prior to becoming a professor?
Okay. I studied computer science and physics at Leipzig University. That's basically where I spent a bunch of my lifetime. And post that, so basically my master's, I looked into what we used to call personalized information spaces, which was all about taking information retrieval models and making them or ensuring that they're actually taking the background of the user into consideration. That basically led me to pondering how to structure data in such a way that the meaning of the data is also available to the end user. That was basically the topic of my PhD. Was all about knowledge agnostic knowledge extraction models. Yeah, and after my PhD, I'd spent a little bit of time in academia, actually leading a research group, and then took it from there to being a professor.
What led to your passion for knowledge? What sort of gave you that spark?
Oh, that's a good question. Um, so my mother tells me, I can't really remember all the details, but that I used to ask a lot of why questions. I've always been interested in the why of things. Uh, so yeah, I guess that's still the same. I haven't changed much since being a little kid. I've always been interested in almost everything. I always wondered how things work. So yeah, and it just happens that I'm in the computer science field. I wonder how things work there.
Okay. Um, I've noticed, just an observation. I've noticed that a lot of people that work in knowledge representation and
Mhm.
knowledge graphs, um, they're not in the field because they hate knowledge. They're in the field because they love learning and they love sharing that learning and they love making sense of the world as if it's one big
Mm,
puzzle. So I really appreciate that attitude. You have deep expertise, as you said, in knowledge graph, semantics,
mm,
graph database, and you said a particular phrase that to me was particularly interesting because I've never heard it before. Anti-hoc explainable machine learning.
mhm.
So, can you help us get a little bit more familiarized with the context of your area of expertise? Let's start with maybe graph data structures, and we'll work
Mhm.
out how that works in different areas.
Of course. So I guess foundationally the question here is why graphs? So why do I work with graphs? It turns out that graphs are really a very natural way of representing a lot of the data out there. One of my favorite examples, and I stole this from one of the presentations of Michael Bronstein, really, is if you consider sets, for example. Sets are made out of elements. They don't really have a particular order, but then there are also no edges between the elements of a set, but basically sets are graphs because they're just a very specific or very special type of graph where there are no edges, right? And you can show actually that a lot of the data structures we have out there, lists and so on, they are all really just an instantiation of graphs. So it turns out that because graphs are a more generic or a very generic way of representing data, it just made sense to look at learning on graphs as the less or the more general framework for actually machine learning on any type of data with structure to a certain degree. Um, it also turns out that graphs are a very when I say graphs, I don't mean histograms, I mean networks, just for people who do more network theory. Yeah. So what I was saying is they're a very natural way really of representing data, but it turns out also that learning on graphs can hence be put down or extended to learning on a lot of other different types of structures, such as sets, lists, and so on. So it was just a very natural approach towards having generic or generalized machine learning algorithms. So that's one. So why graphs?
So graphs is the most generalized, the most expressive way of representing information, data, and that gives you the flexibility of applying it to any kind of structure because it's so
I wouldn't
flexible.
say the most. I would say a general way, because the most would assume that I have a generalization function, and then I can say that's really the argument that maximizes that function. I would not want to claim that, but it is a very natural way of representing a lot of data out there. The way your brain works, for example, the cells in your brain and the connections between them, or if you think about transportation infrastructure, those are graphs as well. You can move it to really a lot of different domains and find that a very natural way of representing the data there is a graph. So having algorithms that work on graph also allows to go across a lot of domains, and that's usually quite helpful.
So what would you say, out of curiosity, is a
Yes.
more expressive or a more flexible data structure?
A more flexible data structure than graphs? That is a very good question. Well, there are generalizations of graphs out there. There are hypergraphs, for example, or labeled hypergraphs, which basically go beyond the standard network structure and actually say, well, in a hypergraph, you can have edges which do not only connect two nodes, but n nodes. And in a labeled hypergraphs, you have those edges, you can actually add decorations to them. So add further attributes to the edges, and so on and so forth. So you can create an infinite hierarchy of complexity on top of graphs to go beyond the type of networks that we usually use. So I would suggest that, yeah, that is a very, very flexible way of representing data, but it's also, in some cases, too powerful, because it basically adds a lot of implicit degrees of freedoms that the machine learning algorithm, for example, has to consider.
Okay, I'm ill-equipped to further traverse through that conversation, but I will certainly take that as food for thought. So let's talk about graph databases, how they store graph data, and
Mhm.
what's their relationship to knowledge graphs.
Okay, so because graphs are so flexible, so networks, one way to represent really data that's available in the world is via the simple principle of representing assertions. Assertions basically being triples, where you have a subject, the subject of the assertion, then you have a predicate, which is really the relation between the subject, and the third part, which is really the object. So what we often do in knowledge graphs is we say, all right, we are going to represent the knowledge in a particular domain via a set of assertions, and each of these assertions is going to be one of those triples. So it turns out that that particular representation of knowledge can't be regarded as a so-called regular hypergraph, but a regular hypergraph in the sense that every edge connects exactly three things: the subject, the predicate, and the object of a particular assertion. Um, it turns out that because the structure is regular, we can actually map it to a different representation. That's basically what actually brought me to the area of graph databases. So if you look at a regular structure which only has three parts, that structure is really equivalent to what we would call an order 3 tensor. And you can think of tensors really simply as an extension of matrices. So if you remember your linear algebra, uh, probably your professor came and said, oh, that these things have dimension 0. Those are points. And then you can take a point and extend the number of dimensions. And if you look at dimension 1, oh, you then have a vector. And you look at dimension 2 or 2 dimension, then you have a matrix. Well, if you add a third dimension, you have another 3 tensor. It's actually pretty simple. But then you can take that representation, so just think extension of matrices, and show that it's really equivalent to this graph type representation or network type representation. But because we can store data that way by swapping the representation, we can actually now operate on that graph as if it were simply some form of linear algebra. So basically some vector operations. And the reason why I went into graph databases was that when we used standard relational database techniques, to query very large graphs, think about graphs that contain a billion or 10 billion assertions, it simply didn't scale anymore. The runtimes were terrible, you could not inject semantics, and so on and so forth. But by swapping the representation to really this tensor representation, we were able to show that the operations which are necessary to query large knowledge graphs can actually be represented by very simple operations on these tensors. And we can hence run classical query operations 10,000 times, or even sometimes even faster than that. So the larger the knowledge graph, the larger the gain, really. It doesn't only have an impact on runtime, it also has an impact really on the CO2 output of our algorithm. So I'm quite concerned with the way we use energy, really. I am a researcher. I do believe we should use energy for the right purposes. But if we can have efficient algorithms that have a lower energy consumption, we should work on that and develop that. So how did one guy put it? There was a school in physics that was shut up and calculate. So don't think about the repercussions of what you do. I'm not of that school. I'm more of a shut up while you calculate. But as soon as you're done calculating, make sure that the impact makes sense, right? So have the theory part, but also have the pragmatic part of things sorted out. And yeah, so that's what got me there. And I can get into technical details if you want, but fundamentally, the graph databases that we build are faster, more efficient, and they then allow, and that brings me basically to your first question, the whole idea of anti-hoc explainable machine learning. So because we now have fast graph databases, it turns out that we can replace certain operators which were used in the past for learning on structured data. A little bit of history here. The way anti-hoc machine learning or explainable machine learning was done in the past, especially on knowledge graph-like structures, knowledge bases, was you would have a bunch of data. You would select some nodes and say, these are my positive examples. Let's be very practical here. We take we imagine you have a knowledge graph of places on the planet. So you have places, you have their mayors, you have their location, the city, the countries they're in, obviously information about the countries, and so on and so forth. And each of the statements would be an assertion. Take such a knowledge base, and you're presented with a bunch of positive examples: Paris, Dublin, Berlin, and a bunch of negative examples like Bafusam, Sydney, and let me think, Köln, or Cologne in English. And you're then asked, find a classifier which classifies these positive examples as positive and these negative examples as negative. Back in the days, what we would have done would be to use something like a so-called refinement operator. It's just a fancy word to say we'd have had an operator that can search through the space of hypotheses in a structured way. And the way it would do that is it would generate a bunch of hypotheses, but you'd have to test its hypotheses, and the hypotheses would be tested using a reasoner. I'm getting there. I'm almost there.
No, it's fine.
The thing with the reasoners is that reasoners are slow. So if you take a query to a reasoner, commonly call a class expression, let's say cities located in Europe would be a class expression in my example. You would send that to a reasoner, and the reasoner would basically have to churn through the data to find all the instances of cities located in Europe. And usually that takes ages. And that also means that learning on knowledge graphs was really expensive and hence not used. What we've done is, because we now have this really fast triple store, we can actually replace this idea of using a reasoner by use a triple store instead. So the queries don't go to a reasoner, they go to a triple store, and we can answer them fast, which means we can now learn these class expressions on very large data sets. Why is that important? How is that anti-hoc explainable machine learning? Now, what is a class expression? A class expression is really nothing else than the description of data. The cool thing about it is, number one, it can serve as a machine learning model. So you think about my example, the example I had before, those were basically capital cities in Europe, right? So you can write a logical expression which says capital cities in Europe and transform it into natural language, which means that an end user will actually know this model fetches for capital cities in Europe. And the end user could say, yeah, this is exactly what I was looking for. This is exactly the concept I wanted to learn. Or say, what are you doing? This is not what I want, and reject that option. So we basically give full information as to what the machine learning system is doing to the end user. We don't do that post hoc, ergo post the creation of the model. That will be post hoc machine learning. We do that during the learning, or basically the conception time of the model, hence anti hoc explainable machine learning. And because we can verbalize everything that is in the logical expression, we ensure that users have full control over what they really receive as outputs from a machine learning model, because they actually can understand not only the model itself, but also the genesis of the model, so how the model was created across time. That's really what we mean by anti hoc explainable machine learning. And with that, yeah, we basically just give the user the control back on over their own data. That was lengthy.
No, it's good. A lot of food for thought. I'm going to try to address my observations in the way that you spoke about them. First, you wouldn't have said physics at some point, that the physics background smell or the cooking process would have permeated the conversation. And I see that your view of calculating and experimenting and boiling down these calculations, it's very much applied mathematics. You know, when you have vectors and matrices, it's all influenced by physics. And how do you boil it down to the most fundamental mechanical way of accomplishing the task? I think it's really important that you question the way things have been done, because if people are just building on top of people's work and someone did the brutish way of calculating it because that was just the most available means of solving the problem, 100 years ago, what the hell are we doing? Because now we have access to higher technology, more performant hardware, richer, open source systems that we could just get and create systems. But if we're fundamentally having a brutish approach and a system that greedily consumes resources that could otherwise be reduced just with more efficient algorithms, more efficient ways of processing that information, we should be looking into those novel ways of increasing the performance, the efficiencies of systems.
Absolutely agree. Yeah.
There's no reason why we shouldn't just look at the cosmetics of, here's a more performant way of a natural language query, rather than, okay, we're burning a lot of energy. How do we reduce that to a tenth of the magnitude? Really?
Yeah, I mean, you're talking about the 10th. That was one of the interesting things, really, when we try to really measure the amount of energy consumption that machine learning or knowledge graph really brought about. It really did turn out that roughly 90% of the time was spent in the reasoner, and that's really what we wanted to reduce. So we reduced that to 10 to the minus 4. So basically, that doesn't play a role anymore. So we only need 10% of the energy. So yeah, that's exactly where we want to go. And I totally agree with you. That's something that we need to do as a domain of research. Not only think about, yes, we should have correct and complete algorithms. Don't get me wrong here. But once we have that, we should also think about what's the impact of those algorithms and how we make it better.
I appreciate the pragmatic and forward-thinking way of designing the architecture of the underlying system, of the underlying engine of the system. You said, I want this, and I want this, and I want it to be really cheap, energy-wise, and it should tell you how it works. I mean, that's the most efficient way of designing exactly the positive outcome that you want. And you mentioned this is also a way of baking in, not only, like, okay, normally the scenario we're painting here is, normally people make a model or make an assumption, they feed it data, and that model shapes according to however it believes the data is kind of related to each other, right? The training data informs the model becomes a structure, and then you go inspect the model and you say, okay, this is right or wrong. Normally that's the way of training a machine learning model.
Well, yeah, normally you have test data, and you basically use your test data to say, okay, this is the performance of my model. And it works well for certain applications, to be totally fair. If you think about large language models, great. And they're commonly based on black box models. But there are a lot, especially in the domain of critical applications or engineering, any place where you have what we used to call knowledge workers, people who are actually well informed, who know their domain really well, and are actually able to tell you whether what the model learn makes sense at all. In those areas, explainability is key. That's number one. There's a paper which came out last year which actually measured that. And number two, by getting feedback from the end users, you can actually improve your machine learning system. That's basically kind of meta feedback, because you can have, back to the example with the cities, if you think about somebody who's an expert in geography, the person could actually say, well, that's not really what I was looking for. I was actually looking for cities which are located on this particular plate or the like. And that would basically then go back into the hypothesis space, so that with the next geographer, one would actually give those type of explanations a priority. So it actually also improves the learning, or the type of learning that such systems can actually carry out.
Well, I was going to say that anytime you encounter a black box system, it makes it less maintainable and it makes it less trustworthy, because we're making all these implicit assumptions as to how it's actually functioning. But we might get false positives for a very long time, and we might make the assumption that the data that we're using to train these models is healthy and accurately annotated or whatever. But I see the way of having a white box model, of baking in the model and the training data in the same space, to just be the most to be a superior way of reflecting that operation. Show your work so people can see, have you made a mistake or not? Did you add the zero or not? Did you multiply correctly or not? The proof is in the pudding. It's in
Yeah.
the calculation.
I completely agree, and I do think, that with these algorithms, we found a way to actually make that happen. So that you mentioned trustworthiness, and that's also something that's super important in critical applications, especially if you think about biomedical doctors. A model that would say, okay, it's time to amputate that leg. Yeah, it's time to amputate the leg of the patient. I mean, you might want to be able to double check why that model tells you that somebody needs to lose a leg, right? Lose a limb. And yeah, that's exactly what we're interested in, making sure that the experts, the human experts, actually can exploit machine learning, but actually also know what's happening. Totally. I'm totally with you there.
I'm a firm believer that systems need to be transparent for them to be useful, because if you're just getting fed instructions, not everybody in the world has their reasoner baked into their head. So they sometimes just blindly take the instructions and maybe perform incorrect results or incorrect actions based on those instructions. As you said, maybe a healthcare system that recommends surgeries is faulty in nature, and the surgeons are just cutting people up because the system told me to, like
Exactly.
the engineers knew what they were doing. I'm not responsible, but inherently we're all responsible, because we're all part of a system that we're trying to create, that we're trying to create a better society, to be more efficient, to lift the expertise of humans, put it into a machine, and fortify, how do we run a healthy society, right? That's the whole point.
Yeah, absolutely.
So I want to get into your impressive track record. You're an incredibly accomplished academic contributor, and you've contributed to over 400 papers and presentations in various conferences. You've been a recipient of over 30 awards. How do you manage to do all that? Where do you find the time?
Oh, that's a very good question. I don't sleep much. That's not necessarily the best thing. So don't copy me there. But I'm just really interested in the topic. So as I mentioned, I've always been a very curious kind of person. I was curious as a kid. I'm still curious now. I haven't changed much since I was a kid. So and I'm very, very interested in the things that I do, and I'm very lucky and fortunate to be able to do them and really get paid for it. So it's fantastic. And But I'm also very lucky to have a bunch of people working with me who are also very curious and can basically bounce ideas off them. And yeah, we don't mind going the path that has not been followed or explored. Yeah, and that does bring about interesting results. I mean, quirky results in some sense, but very interesting. An example being this whole idea of let's look at graph databases from a tensor perspective and actually say, hey, if it's a tensor, then the classical graph operations must actually be linear algebra operations, and suddenly it works. But these kind of jumps are what I think characterizes my work most.
It also appears to me that you are someone who's willing to let somebody take it upon themselves to explore the subject
Yeah.
matter. I mean, research is sort of analysis, synthesis, and then experimentation. So some people like to rule with fear and I know better, but it's really like go explore, right? It's a period of just here's the hypothesis, find the most reputable sources of evidence, and figure out how to chart that course. There's the map, there's the compass. You got
No,
this.
absolutely. Absolutely. I see myself more as a facilitator. I mean, I am curious. I want to understand things, but and other people are curious and want to understand things. So why don't we just get together as a research group and try to understand things? That's kind of the fun. So yeah, I mean, there are roles in academia, and it's my job basically to kind of shield my PhD students and postdocs from some of the, let's say, more tense and annoying parts of academia, but so that they can actually have fun and actually figure things out just for the sake of why not, right? So yeah, I totally think that's kind of the direction we need to go to. I also think but I mean, it's not only for my own sake. I think if we build a society of people who are burnt out because they've not been able to actually do research, they've been busy doing a million other things, or basically being scared and frustrated by their research because they're not interested in it or they are forced to do things, it just doesn't get us anywhere. So yeah, I don't want to live in a society of zombies, and I'm just trying to kind of do my share, hoping that yeah, we can, as a jointly as a society, rather create a society of people who are interested in want to get to know stuff and do stuff, make things happen. Pretty simple, actually.
Yeah, that's a healthy perspective. How are we supposed to create novel solutions to old problems if we're afraid to make mistakes and take
Yeah,
chances and explore and
exactly.
get our hands dirty? Um, you are a Next Einstein and a Lamarr Fellow. Can you explain to me
Correct.
what a Next Einstein is?
Yes, of course. So my parents are from Cameroon. I moved to Germany when I was 15 and basically spent most of my life here. But my roots are still there, of course. And the whole idea behind the Next Einstein Fellowship was really that there was an observation that, and I might be wrong on my numbers here, but African countries spend less than 2% of their BGP on research, which basically means that foundationally, researchers on the African continent really have quite significant challenges getting their work out, or actually even working on things that are of international significance. And the whole idea behind the Next Einstein Fellowship was actually creating this link between high performing researchers and really the African continent. So that's what it was all about. Within my term, I had the pleasure and honor really to talk and work with a lot of young people, young African scientists, and actually ended up hiring quite a few of them because they're really fantastic people. They're really interested in their work, and because of those hurdles, they're even more passionate about their work. And I was really an is an honor to have been able to give the opportunities and the resources to actually push that further. So yeah, that's what the Next Einstein Fellowship was really all about. It was recreating these links, and from my perspective, was really a catalyst towards offering opportunities to others who have not been as fortunate as I have been. And the other fellowship, the Lamarr Fellowship, that's really about research. So it's a fellowship of the state of North Rhine-Westphalia, one of the federal states here in Germany, and it was all about giving high-performing researchers in the area of AI and machine learning the possibility to actually have look into areas of research which they would otherwise not really be able to look into. So one of the things I'm interested in is really revisiting how we build large language models. Turns out that that's super cool. I'm a big fan of large language models. I actually have one running here right now, and I fool around with it all the time. But one of the things that they're really bad at, and that's there's a bunch of literature that talks about that, is actually factual knowledge. And my area of specialization is knowledge graphs. So my foundational question has always been, how do I take a large language model and actually make sure that it's good at factual things? And that's really what that whole project is about, merging these two views on human knowledge, with the hope that we can create large language models which are actually reliable and trustworthy to actually use them in their downstream applications in combinations with the knowledge graphs that I work on.
Okay. First, power to you to open up opportunities for people in Africa as well. You know, you came from there and you want to just pave the way for other minds to have the resources to explore and be able to contribute to the scientific field. I really appreciate
Mm-hmm.
that. I'm originally from El Salvador, and
Mm-hmm.
for a very long time it was just riddled with very violent crime and gangs and things like that. And I see the raw intellect of my people to be, pretty astounding. There's a lot of
Mm-hmm.
astuteness in this space, but lack of resources makes people be makes people become a consequence of their environment. And
Yeah.
I consider that to be a huge pity because
Mm.
who's to say we didn't have a little bit more infrastructure in place to just feed the minds a little bit more? What could come out of that? Like the it shouldn't be centralized in specific areas of the world. We should be able to have all the bright minds around the world to fully utilize their potential. But
I totally agree. Yeah, yeah. So I was in Mexico a few weeks ago, and I looked at some of the Mexican art, and I was like, "Blimey!" Like it has taken geniuses just to write down the languages and all the symmetry in the art. It's just really really cool. And I'm also talking to people in Colombia, vis-a-vis actually doing joint research on a problem that's actually quite important across the world, which people don't consider much, which is acute kidney injuries. Turns out that a lot of people die actually in hospitals. Acute kidney injuries.
oh, kidney.
Yeah. So it turns
Okay.
out that it kills a lot of people, especially in Colombia, um, simply because it is really hard to predict whether one should stop treatment on that particular type of injury or not. And there's the data is there, but the infrastructure is not there to actually run the types of machine learning algorithms that one would have to run to actually have a model which predicts that correctly. So yeah, I'm always interested in not only building things that work, but actually applying things that work to real life problems. Because I think at the end of the day, before being a researcher, I'm a human. But
It'd
I think
be
that holds for all of us.
No, I appreciate that. Yeah, it'd be nice to have clean water everywhere too.
Oh
just
yeah.
that, just talking about how to apply useful ideas into society. It'd be nice to have clean water in countries everywhere.
Let me ask you a question. How would you do that? Give me ideas.
Well, I mean, you see the technology already exists
Mm,
for creating composite materials that can be used to create filters and things like that.
mm,
To make potable water. Just in the American market, I see coconut fiber filter systems that you can embed
mhm,
inside of your water supply.
mm,
And I don't know how they do it, but the way that they create this from gravel, activated carbon,
mm,
charcoal, uh, and coconut husk. What is one of the main exporters of these countries of Latin America?
mm.
Coconuts. So why the
Right.
hell is that raw material which is considered to be a waste product, not reused to
mm,
create water filters and
mm,
deployed in a reusable infrastructure, or at least these given to different households and regions that suffer a lot of disease. Why is
mm,
that not distributed? I mean, there should be some sort of social impact system there to take
mm,
these waste products,
mm.
repurpose into filters, repurpose into these modular systems that you can just employ into like the infrastructure.
Yeah. No, I totally concur. How does one do that best? It I've thought about if solving a few societal problems with machine learning. It always turns out that the amount of resources that one needs to make that happen is tiny compared to what the government can
Yeah,
offer.
it's
But
not a big problem to solve.
yeah,
3D printers are now 300, like the household 3D printers are
yeah,
$300.
correct.
A press, just putting something heavy on something to make a mold.
Yeah,
You just need something heavy. You could use rocks, whatever, like the way to create the infrastructure to make a crude factory
mm,
and then deploy that and construct that, it's relatively inexpensive. For $10,000,
mm.
I could probably go build a factory. Actually, you just gave me a to-do list. For $10,000, next $10,000 I get, I'm gonna go build some sort of coconut fiber filter factory. Why not?
If I
Uh,
can help, let me know. That sounds like fun. Let's make it happen.
cool. So let's go back to the conversation, but this is certainly a nice side quest to tackle. Um,
Mhm.
so you're based out of Germany, and you said you've been
Correct.
there since you were 15. What Yeah, what was it, that change in culture like? And, what are some of the virtues of being in Germany?
Ooh, that's gonna be a long answer. So I moved to Germany in 1999, and I moved to East Germany. That I have to point out. Um, and over the last 25 years, quite a bit has changed. So I remember, just the truth of the matter. I remember encountering quite a few different Nazis, for example, while coming from university, or I think the most interesting one was I was writing my PhD thesis and getting stuff done. It was 3 a.m. and I was coming back from work, and I just heard people saying things that were really atrocious, um, pretty disgusting stuff. And being in the realm of math at that moment, I really didn't realize that they were addressing me. So I just took my tram. But by looking at how they were staring at me, I noticed, interesting. This mindset is still there, which is a shame. But over the last 25 years, that has changed quite a bit. So it was getting significantly better. Things were just easier to navigate, put it that way. But over the last few years, and that's been a movement, I think, across all of the political systems, there's been this move towards the extreme right again, which is actually quite, it's not only a pity, it's a shame, because really a lot of the things that we've worked on building as a society over the last 20 something years are now being not only rejected but destroyed. This spirit of let's just get together, doesn't really matter what your skin color is or whatever, as long as you're willing to work, let's build this society together. That is just being jeopardized by not that many minds, but many minds that actually scream pretty loudly. So yeah, one of my top goals actually in my research group is to make sure that, or to contribute to not having that type of spirit and just having people who are open and happy to talk to each other. So yeah, I tried actually to contribute by hiring people from very diverse places and just having this melting pot of ideas that can be exchanged. But yeah, that has been one of the major changes, or one of the waves in Germany. There's also been quite a change in the way investment, for example, are done. So because the societal part is working a certain way. The financial part, Germany's been doing very well, but from the point of view of investment and pushing new ideas, it seems to me that we're still way behind. The move, the movement from an idea to actually an investment takes significantly longer than in the US, for example, where you are, where a good idea is often pushed really quickly because time to market, time is money. It's not really the case here. We're still the land of slow thinking, slow thinkers in some sense, very engineering,
Yeah, robust
thinking to
engineering,
come up and say, yeah, but robust engineering um,
rigid.
sometimes takes it's too rigid. Yeah, exactly. Yeah, sometimes you just need to throw the thing out there, check whether it works, and basically fix the things that don't work. So that seems to have quite an impact really on the current economic state of Germany, and I think that we're going to see quite a few changes in that respect in the years to come. So yeah, gives you a rough idea of where we are.
Let's talk about the work that you do in your
Yes.
not in the academic sense, but in the professional commercial sense.
Hmm.
Um, you have you are contributing to an organization called Databorg,
Hmm.
and you are also the founder of Tentris.
Hmm.
So we
Co-founder.
co-founder.
Mhm.
Okay, co-founder.
Yeah.
So let's dive into what Databorg is, and then we can go into Tentris and see how they're related.
Hmm. Hmm. So yeah, sure. The foundational idea behind Databug was actually an observation that seems trivial, and it is simply that the different departments of larger organizations actually don't really use the same vocabulary. That might seem something that's trivial to solve, but it turns out that it is not, because that's also reflected in the data that they use, and because it's such an intrinsic part of the department cultures, it then becomes very difficult to actually bridge across these departments or actually ask queries which go across uh, these departments. So what we are interested in Databorg is really creating this middleware which takes data from all across a large company, from a bunch of really different departments, and puts the data together in such a way that we actually have unified semantics. The foundational idea being that if we have unified semantics, we can actually now query across the borders of departments, across the borders of different semantics, and actually have a holistic view of what happens at the data level, of course, in a company. And that's really the technology in the backend, obviously knowledge graphs, because they are designed for exactly that, for basically unifying semantics and having unique semantics at query time. Now, the question is, where do you put that knowledge graph, and where do you put that machine learning that you basically want to use on the knowledge graph? And that's what Tentris is all about. So I mentioned the idea of representing knowledge graphs as tensors before, and that's really kind of the foundation of Tentris. It's having really fast query algorithms for really large data sets, and having these algorithms perform really fast doesn't only save time, it basically also saves money and saves CO2. So if you imagine having to process a query and paying, let's say, $1 for 50,000 CPU cycles, then obviously it's running half a minute instead of running a day saves you tons of money. And that's really what Tentris is all about when it comes to storage. But then the second foundational idea behind Tentris was really, how do we combine this idea of storing data well with the idea of processing data well? So those are actually two different things when it comes to machine learning. The classical architecture is, I have a bunch of data somewhere. I take the data and I ship it to a machine learning algorithm. Machine learning algorithm computes a model and I ship the model back. That basically shipping of data is not only expensive, also running the algorithms remotely can also be tricky when it comes to the general data protection rule, for example. And the whole idea behind Tendris is, hey, let's just do that in one. Let's take a very fast graph database, design explainable machine learning algorithms that work directly in the database so that we can actually run the whole computation within one environment. Again, it saves time, but it also simply saves money and saves really CO2. So it's significantly greener as a solution. And Tendris is really all about creating these very efficient, very effective machine learning algorithms and storage algorithms, which together then give you a unified solution towards data management.
Pardon my ignorance, but how is this Tentris based on tensors different from RDF and label property graphs?
Okay, so RDF is really tells you, so the resource description framework tells you how to represent data, right? And it actually gives you a query language, which is called Sparkle. And it says this is how to query data. However, it doesn't tell you how to implement these things. So it gives you a formal specification of the semantics, of the meaning of queries. It doesn't tell you how to implement that particular semantics. It's basically the same as SQL and relational databases. You have the SQL specification on the one side, or the definition of what a relational table is, but you can take Oracle, you can take MySQL, and so on. You have a bunch of different databases which implement those standards. Same here, we have graph databases that really implement the standards, RDF, Sparkle, and so on. And the difference between all of these systems is really how they do it. And how we do it, as I mentioned, is really by rethinking the way we represent data and looking at them as if they were tensors, and then basically mapping all the operations to these tensor space where things are way faster, more efficient.
How does this I mean, I think just by virtue of you saying that this is faster to compute, faster to process, explainable within the structure of how it's stored. I think it may answer my follow-up question, but how do you circumvene the problem that many graph databases have, which is concurrent CRUD operations?
That is a very, very technical question, and I'm happy to answer it. So what I've not talked about is really the how we represent the tensors. So it turns out that when you think about the tensor, it's really a huge binary data structure. It's basically a bunch of zeros and ones. And the dimensions, the 3 dimensions are basically the subject, predicate, and object dimension. So representing such very sparse structures, because those tensors are generally very sparse, is something that we've been looking into in computer science for ages. There's this whole idea of a trie. So basically that was a tree-like structure that was used in natural language processing back in the days to actually represent, to compress the representation of sparse structures across vocabularies. What we've done is we've basically moved or extended upon that particular data structure and created what is called a hypertrie. And a hypertrie, I'm not going to get into the technical details. The important bit is it stores regular tensors really well. But because it's a hierarchical structure, it also supports these CRUD operations really well. So we can, instead of basically looking at the whole data when we're doing updates, we can actually do CRUD locally and then use the classical approach of having a journal to remember which operations were carried out when, so that we can actually repair errors if any errors occur.
How does that differ from conventional graph databases?
Okay, so conventional graph databases most commonly rely on structures which were designed for relational databases. So, for example, B plus trees. Now, B plus trees have a particular way of storing data, which basically allow for so-called prefix-based operations. What I mean is the following. If you imagine that you're querying for, give me all the things that John loves. So the query would be John loves variable, and you would send that to the database, and the database would then return a list of things which are such that if you add those things to John loves, so let's say apples, if you take John loves and one of the elements of my list, say apples, you will find John loves apples in the background knowledge. So that's really how those systems work. Now, it turns out that those systems are really good at what are called prefix queries, which basically means that if you want to process different types of queries, so have these variables at different positions, it turns out that you actually need different indexes to process those queries well. It also means that when you do updates, you also need to update all of those indexes. Because we have one data structure which allows you to run all types of queries. So all of the possible positions of variables in those queries. So John loves what? John, what is the relationship between John and Mary? Or what are the things, or what are the persons who loves apples? Those would basically be queries where the variable will move across what we call a triple pattern. Because we can process them all in one data structure, we can basically run the CRUD operations, only need to run the CRUD operations on one data structure instead of several indexes. And that basically makes whole data management more efficient.
Yeah, cheaper, more efficient. Okay, faster.
Correct.
So it makes it safer to do concurrent operations because you anticipate that people are not going to do it in a tenth of a second or something like that. At least it would depend on the architecture and the use case. I would assume.
Yeah. No, but the thing is, the cool thing is you can simply have several copies of the same data. And if you have a lot of concurrent queries, you can actually, it's easier to remember where things were changed in a corresponding journal so that you can do merges. So, and you can also exploit distributed file systems because there's actually only one object to manage and not 16 of them. So that just makes life significantly easier having data stored that way.
Okay. I had a previous conversation that really dove into this topic. Hence, I
Mhm.
thought I would ask because I know you've
No,
put a
of
lot of
course.
thought into how to mathematically model and really reflect the most efficient way of doing this. So thank you for giving me an explanation that I'm not ready to seep into my head, but I will review this in the future and try to make better sense of it. So what are some case studies? You say this is something that's more performant than what's
Mhm.
commercially available by a
Mhm.
magnitude of 1.8? No, or
Magnitude, it depends on the data set size. In our experiments, we've been up to 10,000 times faster than some of the systems which are available out there.
just that, just 10,000.
Yeah, no, we're working on it.
So what are some of those applications? Like deploying really advanced sensors for scientific research, or like where would you
So,
need to have a really advanced means of absorbing or collecting data and then processing it and then baking that
so
into the machine learning model?
there are really mundane applications, for example, in the domain of e-commerce. So if you think about having an intelligent recommender system, there are large companies out there which have a lot of products. I mean, I guess I can say company names here, but if you imagine that you go to your Amazon profile and you really want a recommender that looks at all the data which is available out there, you're looking at billions and billions of assertions. And having a recommender that's able to learn your preferences and actually explain why it recommends a certain product.
That'd be
That's
cool.
one of the applications, applications we are looking into. Where we've applied this really in practice was in a project with Siemens that I can really say. And there the idea was actually if you imagine that you're building a production plant, you actually want to ask the question, what is the best way to do this? So if I know a bunch of components that I can use, but I also want to be able to predict what those components can do and cannot do for my particular engineering use case. And it turns out that you can actually use those algorithms there based on the specification, basically on the very formal specification of in output behavior of components. So those algorithms were able not only to predict what to use, but basically how to use those things best. A domain where we also are looking into applying our algorithms is in the biomedical domain, especially in the drug design and drug repurposing domain.
Mm.
So in the whole area of chemistry, it turns out that chemistry is very special in the sense that the type of data items that chemists use, molecules in general, they have an internal structure, which means that they're intrinsically structured, but they can also combine to create more complex structures. So most of the machine learning algorithms that we have out there assume flat representation, so basically vectors. Well,
Mhm.
it turns out that those particular structures are not particularly. It's not that easy. I mean, there's
They're
obviously
shapes.
graph-based,
They're
graph-based machine learning
properties.
and the like. Yeah, but actually, our models, because they're designed for structured data, are actually particularly well suited to that domain. So one thing that we've done is actually aiming to predict the how cancer, basically what the likelihood is that a particular molecule leads to cancer. And it turns out that by using structured information, we can actually predict the characteristics of such molecules. So a classical model would basically just say, this is the probability that this particular molecule will give you cancer. Whilst we say this is really the substructure in molecules which is responsible for you getting cancer if you touch those types of molecules. And with that, actually, we can now start a dialogue with people who are chemists, and they can say, well, yeah, this makes sense. Oh, this is absolute nonsense. I know a bunch of molecules which don't do that. Please reject this hypothesis. And that's again where human expertise and machine expertise come together to actually create better models. And as I mentioned, what we are looking into is actually using that into drug repurposing. That's a domain that is very dear to me. So, for example, roughly 1 million people die each year of tuberculosis. And the reason is not that we don't have corresponding drugs for that. It is that there are patents on these drugs. And it becomes a problem when one wants to have a cheaper factory produce those drugs. If those cheaper factories, cheaper doesn't mean worse quality product. It simply means that the
Less,
cost
less
is lower. Yeah. Well, it becomes a problem if they don't have access to the patent. So you have people die, although they wouldn't have died if the drug had been produced or created, manufactured somewhere else. And my goal in that respect is to basically have these algorithms ensure that drug repurposing, for example, is way easier. Because if it were easier, it would basically mean that we could save simply more human lives. So that's an area of application that is very close to my heart.
Who should reach out to you?
Who should reach out to me? In which context?
Entrepreneurial context.
Okay, who should reach out to me? Anybody who really has any types of needs vis-a-vis more efficient data processing or explainability of data processing, extraction, integration, fusion, or basically, of course, at the application side, so basically downstream applications. Turns out that the algorithms that we've created are very generic, so they can be used across a bunch of verticals. But I think like the biomedical domain and the e-commerce domain are domains where the amount of data and the variance across the different data is such that our algorithms are particularly well suited to basically run.
Okay. And do you have any advice for someone who's entering into the space of science and just business, just applying this scientific method of doing the thing, gaining evidence, gaining confidence, eliminating bad hypotheses? Do you have any idea on how you can share your experience with that person?
Of course. So this is not my first try towards basically entrepreneurship or the like. And it turns out that in a lot of cases, the self-bias, although I'm aware of the fact that self-bias exists, self-bias is actually pretty brutal because one lives in this bubble of science and does a lot of research, which is super cool in that bubble. But actually trying to get into applications as early as possible is something I would always suggest that people do. So really, don't take your assumptions for granted. Really, just try them out. It will lead to a lot of assumptions being rejected. It will lead to having to go back to the blackboard and rethinking a lot of things for sure. But it actually leads to practically viable results that can really be used in practical settings. So diversify, that's one. Basically, don't only ask one company. It might just be that the result is a bias of the company. Diversify the type of companies or entities you work with, but on the other hand, also be ready to simply rethink your assumptions and you're ready to go.
Okay. Any last words to the audience before we conclude the call?
Thank you all for listening. This has been a blast. Thank you for having me. I've really, really enjoyed this. And yeah, let's create that factory. It's going to be fun.
Yeah, for sure. We'll keep you guys updated. Thank you. Thank you, Axel.
Thank you very much. Yeah, have a great day, everybody.